So I moved it here, more or less the same thing. So we have a compact set, and then we have a subset of it. What I know about E is that it is infinite only. And my claim is that K contains at least one limit point of E. So it means that the intersection between the set K and the derived set, which contains all the limit points, is not empty. Okay, so a sketch of a proof. So we assume to the contrary that E prime intersect is empty. So in the language of set theory, but if you want, it means that none of the elements of K is a limit point of E. And we want to explore the consequence of this assumption and arrive at a contradiction. So I would say, because I want somehow to use my compactness assumption, and you have some experience now, I would say let us start with some kind of open cover for my set, okay? So I would say let Q belongs to K, okay? Okay, so Q belongs to K. Then, because there is no intersection between K and E prime, this means what? This means what? Q belongs to K, so this means that because E prime and K is assumed to be empty, Q does not belong to E prime. So this means Q is not a limit point of E. Yes? Q is not a limit point of E. But what is the meaning of not being a limit point? So being a limit point means what? So let me go and recap something. So when you say Q is a limit point, this means what? This means for every epsilon positive in the neighborhood with radius epsilon around Q intersect with E minus Q is not empty. That's the meaning of Q belongs to E prime. But Q does not belong to E prime. What is the translation? This is just mathematical logic. What is the negation of universal quantifier? Existence. So there exists an epsilon greater than 0, such that what happens? Negation of this one. Such that n Q sub epsilon intersect with E minus Q is empty. So these are the things that you should be good at it, because this doesn't rely on that. It doesn't depend on analysis or algebra. That's just mathematical logic. So if this is the definition of a limit point, Q belongs to the E prime. This is the definition. Q does not belong to E prime is the negation of this one. So I have to negate this statement. The negation of a universal quantifier is existential quantifier, and then I have to negate this statement, which becomes equality. Is that right? Okay, so when you say that Q is not a limit point, what the conclusion? So therefore what happens? Exactly what I have written. There exists an epsilon, but this epsilon might depend on because Q is an arbitrary element chosen from K, so this epsilon might depend on Q. So that's why this time I want to equip it with an index Q. There exists an epsilon which might depend on Q such that the neighborhood intersect is empty. Yes? Are you following or not? So I just translated this one. And the only difference that I made here is that I equate my epsilon with the next q because I want to do because I want to say this for every q, not just one q. That's why I equip my epsilon with q so that you can see the dependence of this epsilon with that q. Okay. Now, on the other hand, do you see the cover now based on the experience you got from the first theorem? On the other hand, what can I say? Let me write U equals to is an open cover for K. Can you feel this gap? The reason I expect you to tell me because you have some experience in the first theorem. I did something very similar. I picked one Q in K and I grant the existence of a neighborhood around that so that it will not intersect with E minus Q. In this case, because Q is outside, it doesn't matter if I write E or E minus Q. So now I change this Q to this Q. This Q is also in K, it's also in E. And I do the same thing, something like that. So I will start piling up these neighborhoods corresponding to each one of the points in K. Can you fill up this now? Yeah. All these neighborhoods, yes? So neighborhoods Q, epsilon Q, such that Q belongs to, do you agree? Is an open cover. Okay, but because K is compact, what can I conclude? I can conclude only finitely many of them will cover K. So this means K, by the way, in the exam, don't write it like this. This is a sketch of a proof. So you have to write it in words, okay? But you understand what I mean now. So K will be covered with finitely many of them. So it means that there are n of them, for example. Yes? You see, this is a sketch of a proof. So in the proof, you have to be a little bit formal. Is that right? But this is a contradiction. Can you tell me why? It's a little bit subtle contradiction. So which part of the theorem I haven't used so far? Which I emphasize is very important, otherwise it is not correct. I have used compactness because of that, but I haven't used this infiniteness. So it should play a role, otherwise why they should mention it. Okay, let me make it clear for you. So now, do you buy this one or not? So this one is not a contradiction. This now becomes a contradiction, okay? So, but do you first of all agree with this one I am writing? Yes? Because E is a subset of K. This K is a subset of this. E should be also a subset of this. Yes? But this is a contradiction now. And this contradicts E being infinite. That's why infiniteness is important. Why do you think that's the case? Go back and look here. Every one of these that you see doesn't contain any element from E except the center itself. Yes? So this means that on the right hand side, so if I ask you how many elements of E these contain at most? No, this one. Only one. Yeah. This one. Yes? Only every one of them contains at most one element from E. Because you see that when you intersect it with E minus the center, it becomes empty. If you put the center back, it means that at most one will be increased, so that it will be one element from E at most in every one of them. So in the right-hand side, how many elements of E you can have here at most? This will contain at most 1, the next one will contain at most 1, and the last one contains at most 1. So the right-hand side contains a lot of points probably, but from E it contains at most n points. And then E, because it is infinite, cannot be a subset of that one. Is that understandable? So infiniteness becomes important. Yes, but this is a very important theorem to remember. Okay, by the way, do you see that compactness is also important?
Yeah.
So for example, I don't know, so do you remember this set? Let me just give you an example. If I give you this set, 0 to infinity, do you remember last time we had something similar to this? You remember this is compact. Yes? For example, I can consider these open covers, these intervals from -1 to n. If I union them, it will cover this set. And there is no open subcover. There is no finite subcover for them. So this is not compact. Not compact. Okay? But this set, do you remember? This is a very famous set in metric spaces. Do you remember this set? 1, 1 over 2, 1 over 3, etc. Do you remember what was E prime?
0.
Only 0. Okay? So this set is infinite. And do you agree this is a subset of K? But because K is not compact, this theorem is not working. Because E prime is 0, but 0 does not belong to K. So K does not include any limit point of my set. Do you understand that? So compactness is very important. This is not compact. This is a subset of that one. And you see this set does not contain any limit point of my set because the only limit point of this set we learned before is just 0 and it doesn't contain it. So this means compactness is actually important because if you relax compactness, this might not work. And I don't know, for some reason I didn't even put this example in the notes. Might be that's a good one to remember. Any questions? Is that understandable for everyone? Okay, so let us go to the next one. This is a tricky theorem, and then you will see that it seems very innocent. So we learned about this one yesterday. So let me show you the question, the slide. Every closed and bounded interval, closed bounded, is compact. This very simple innocent sentence has a very long proof, and it's a technical. I want to go through a sketch of the proof for you, at least feel how it works. But you see that last time, do you remember? I don't know how many of you remember. What is your opinion about this open interval? Do you remember we did this in full detail and showed that this is not compact? Okay, 0 and 1, the open interval from 0 to 1 is not compact. And it is not hard. We did it in just 1 minute to prove that this is not compact. Okay, but then this theorem tells you that if you change it to this one, suddenly it becomes compact. Okay, and so you might say, first feel what is that much difference that makes this one compact but this one is not compact. Okay? Okay, so this is what we want to show. I will not be able to go through the proof in detail, so I have written it in a very extensive way in the notes so you can study that yourself, but I will try to capture all main parts of the theorem. Okay? Because that's one of the theorems that you should see how the people prove this. Because you know that proof, if you want to prove compactness, do you feel it is hard at least? How you should prove a compactness, you should imagine all possible open covers of the set. You don't have any clue what kind of open covers we will have. But we want to say that no matter which one you choose, you can always choose finitely many subcover for it. It's a very broad, compactness is not something easy to prove in general. Okay? So the idea is this. So let me write this 5, and try to explain as much as we can. Okay, so we want to show that A and B, this closed interval, is compact. So this is what I want to show. Okay, we consider two cases. So a sketch of a proof, okay? Sketch. So we want to consider two cases. One case is extremely simple, the case that A is equal to B. Okay? So one case is that if A is equal to B, then what happens? Then this closed interval contains only one element in it, and this is compact. Why? It's finite, and we learned last time that every finite set is compact. So it's finite and therefore compact. Okay? So the interesting thing, of course this is not very interesting because it is just one single element. So the other case is that A should be less than B. Of course, when I write this notation, A is less than or equal to B. So we want to consider this scenario to see what happens. So the tricky part is this one. So if you want to imagine, so this is A, for example, and B, they are not the same. A is less than B. The idea is, I want to prove that this one is compact. So the standard way of proving something is compact is on the board. So what should I start with? I would say let U be an open cover for A and B. We show that what happens, we show that U contains a finite subcover for A. Yes, because I want to show that this is compact, this is the standard way to start. I imagine that I have an open cover and I want to prove that it contains a finite subcover. Okay, this is the tricky part. They define a set. I will try to motivate you a little bit. We define a set E in this way. Includes all numbers in this closed interval, but with this property, that if you start with A and go up to R, has a finite subcover contained in curly. Okay, so yeah, take your time a little bit to understand this mathematical set. So what I am trying to say is that I don't put everything from this interval into this set. I am choosing those numbers from this interval from here to there, so that if I close it here, this is compact. It has a finite subcover contained in it, in U. And what I want to do, my strategy is to try to push this R to the right as much as I can. And then at the end, I will show you that this R is exactly B. I mean, I can go at most to B, so I can reach to B. So what I am doing is that I am saying that from these numbers on this interval, pick only those ones that if you start from A and end at that R, this is guaranteed to have a finite subcover contained in U. But then I want to show you somehow that this R, I can push it forward and forward. Okay, so I would say that, okay, I will pick A. So A is already compact, so I will have a finite subcover. I want to push it a little bit to the right, and then I will grant you that this is still have. Is it possible to cover it with finitely many covers, finitely many open sets? And then I want to show that you can go forward until you reach to B. So that's the idea. Okay, so what we want to do now, first of all, can you tell me why E is, my goal is to show that E has a supremum. This is my goal. So do you have any idea, do you have any questions about the definition? I am choosing those numbers from A to B so that from A to R has a finite subcover. And if you don't mind, because this is a very, very long sentence, let me choose this sentence to be P, okay? Okay, so I want to show that E has a supremum. This is my goal. But remember very, very first lessons in analysis. If I want to show that E has a supremum, what should I show? I need to use completeness axiom. So I have to show that it is not empty, and I have to show it is bounded above, not below is not important for supremum. It's bounded above, it's not empty and bounded above. Okay? Why this is not empty?
It contains A.
It contains A. Because you know, do you agree that A belongs to A and B? On the other hand, from A to A has P, property P, yes? Because A and A is just that one. So this means that A is in E and E is not, so this means E is not empty. Yes? But why this is bounded above? Which elements are supposed to come to E? They are chosen from A to B. So maximally they cannot go beyond B. Yes? So B is an upper bound for E. So this means that because E, so you can write this, E is a subset actually. E is a subset of A and B. So this means that B is an upper bound for E. So E is bounded above. Okay, so E has a supremum. E has a supremum. E has a sup. Let us call that supremum C. Yes? So this was the tricky part. I mean, you have to be experienced to define a set out of the blue. But they had some strategy in mind, exactly as I explained. And then they want to show that E has a supremum. We were able to show that E is a supremum. And I want to finally show that this supremum belongs to E and it is equal to B. So, but this is very long a proof, but I will try to go as much as we can. Okay, but immediately from this one, do you agree what I can write here? Let me write something here. Do you agree with this one now? As soon as the existence of the supremum is guaranteed, my claim is that this supremum should fit this. Can you tell me why? Why C cannot go beyond B?
B is upper bound.
B is an upper bound and C is the smallest upper bound. So it cannot go beyond B. But why it cannot go below A? No, A belongs to E and C is supremum. So A should be less than or equal to C, and this one is. So this is granted, okay? You have to write them down, but you understand that. So I will need that. But the first thing I want to claim, and if you learn the first step, the other ones are very similar. I want to claim that this equality cannot hold. Okay? So the first thing that I want to show is this. Claim one. A is strictly less than C. Okay, I want to show that A cannot be equal to C. Okay, so what is the situation I have now? Here is A, and here is B. I know C is somewhere here, I don't know, for example. But I want to show you, so I want to show you C has to be here, cannot be exactly on top of A. This is my goal. So I want to show that C cannot be here, something like this. C should be after A. Okay, so how should we prove this? I would say that A belongs to E, and E is covered by U. Yes, because do you remember U? Let U be an open cover. So if you want, I can write it here as well. So E is a subset of the union of all alphas. That's the meaning of being an open cover. Yes. So A belongs to E, according to that, and E is covered by this, meaning this. So what does it mean? It means A also belongs to this set. So this means there will be an index, let me call it alpha naught, in A, such that A belongs to O or alpha naught. Yes? But what type of set is O alpha naught? Because that's an open cover, O is an open set. Okay, so what I can conclude there exists in, I don't know, epsilon, so let me call it R naught, greater than 0, such that A minus R naught and A plus R naught is a subset of O alpha naught. Yes? Because O is open, it means if a point is there, it is an interior point. So this means that I can have a neighborhood around that point. But I am working in R. Neighborhoods in the Euclidean metric are just open intervals centered at the point. So that is the reason I can write this. Do you understand that? Yes? Okay, but I want to say something more here. I want to say that there exists an R. This is guaranteed. So it means that if I want to look at it, this is because you know that I don't have any control over R naught. R naught might be so big that it will also cover B. Yes? But what I want to say is that I can keep it less than B. Do you agree? You see, what I'm saying is that because A belongs to O alpha naught, and because O alpha naught is open, it means that I can find a neighborhood with center O, but in R, neighborhoods are intervals of this type, so that this becomes a subset of O alpha naught. Okay? I do not have any control how big R naught is or how small is this. It might be the case, it is so big that when I write A plus R naught, it goes beyond B or less than B. Okay? So what I want to do, I want to make sure that this, oh sorry, this is A plus R, so might be I am confused. A plus R naught is less than B. So I want to make sure that if the R naught that I have, and I am so lucky that it is automatically behind that, below B, I am done. I don't need to add this one. But if I am not lucky and this goes beyond B, I can make R naught smaller, okay? I will not violate this condition because when I make the radius smaller, I make the interval going closer to A. So this will still be true, but this one will also be true. Is that right? Is that understandable for everyone? Okay. So now, if I want to draw a picture for you, then A plus R naught will be somewhere here, and A minus R naught will be the same size here. Okay. So this radius is R naught. Now let us pick this element, A plus R naught divided by 2. Okay? So, do you agree that this A plus R naught divided by 2 also belongs to E? Yes? Why? Because, first of all, it is in this interval. And how do you know, how should I make sure that this is in E? I have to show that A plus A to up to this can be covered with the elements of, has a finite subcover. Yes? Does this have a finite subcover? Which is that subcover?
The same one.
Just O alpha naught. Yes? So O alpha naught covers this one alone, because A starts from here and goes up to here. Do you see that? But this one is one part of this interval, and this interval is covered just by one open cover, open set. So this can be covered by finitely many open covers, or finitely many sets. So this means that A plus R naught divided by 2 belongs to E. Yes? But because C is the supremum, what can I conclude? I can conclude that A plus R naught divided by 2 is less than or equal to C. Yes? But this one implies that A is strictly less than C. Because A is strictly less than this one. This one is at most equal to C. So A is strictly less than C. Understandable? So this trick, we want to use it again and again to this theorem. So I will do one more, and the last one I will ask you to do it as an exercise. But is that understandable? So in principle, I granted the existence of a supremum. Just this is a supremum gives me this. But I want to say, no, this equality cannot happen. If I want to show that this equality cannot happen, I claimed it, and I hopefully convince you that this is not going to happen. But the technique that I want to use here will be also for the second one. The second one, the claim is that C belongs to E. I want to show the supremum actually belongs to E. Okay? So, to understand what is going on, I have to prove two things to grant this. What are those things? Just say it. I want to show that C belongs to E. First, I have to show that C belongs to the closed interval, which in this case is. Why? Because we have this. So this one is granted for C. The only thing I have to ask myself is to show that A up to C has property P. Yes, if I can show you this, then it means that C belongs to E. Do you agree? Okay. I don't know C is still in E, but I know C belongs to A and B. This I know. Yes, let me write. Yeah, let's sketch over. Why? Because you see it here. C is between A and B, so this one is granted. Okay? But then this one itself is a subset. Okay, sorry, that was a mistake I wrote. This was not E, this is A and B. So do you think this will change something here? So yes, this will change this one. Yes. Because U was an open cover for the closed interval. Yes. So C belongs to this one because of that red part written on the part of the board, and then this one is also this. Yes. So what does it mean? This means C belongs to O alpha, alpha in A. So this means there is an index. If you don't mind, let me call the index beta this time. There is an index beta in A such that C belongs to O beta. Yes? But again, the same strategy I want to start with, okay? What I know, by the way, now, I know that B is here, I know that A is here, but I know C is somewhere here, for example. I am sure that C is not here now because we learned that C should be strictly greater than. Okay, now what can I conclude again? Exactly the same strategy. O beta is open. So what does it mean? This means the existence of a delta this time. Let me write it. The existence of a delta is granted so that, can you write it for me? I want to make sure that you are following me. C belongs to O beta, and O beta is open. So the existence of a delta is granted so that what happens?
From C minus delta to C plus
C, the interval from C minus delta to C plus delta is a subset of O beta, yes, but this time I want to make sure that C minus delta is also greater than A. Yes, because this, I need to explain why I can do that. This is granted, but I don't have any control about the size of delta. I just know delta exists. Okay, so it might be very big. So I am going around C. If this radius is very big, at some point it will pass from A as well, if it's very big. Okay? But if it is very big, I myself manually make it smaller so that delta comes inside. Okay? I don't care about if it is coming before B, but I care that delta goes after A. Okay? So this can be granted because if I am lucky and this delta from the beginning works, I am done. If it doesn't work, I make it smaller. Yes? And finally, that a smaller one, I will call it delta. Okay? So this is granted. So now what do I have in my scenario? So C minus delta is a number greater than A. So let us say that this is C minus delta. And then this will be C plus delta, which of course in this picture will go beyond B, no worries. And C is here. And this is C plus delta. Okay? Do you remember I want to show that A to C has property P? Can you finish the proof? I want to show that A up to C has property P. A is here, C is here. Okay? Decompose it into two parts. From A to C, what should we do here? No, this is not it. This is very early. Okay. Now I have to do something more. Okay, so C minus delta is less than C. Do you agree? But what was C? C was supremum of E. There is a theorem I told you. It is very simple. I told you remember it. Okay, we will use it a lot, and this is one of them. If a number is less than supremum, it is I can grant the existence of E in my set. You remember what is that? If I know a number is smaller than my supremum, the existence of an element from my set is granted so that
between
E, yes, is greater than this number, yes, and less than or equal to C. Yes? Where is this E living? In my picture, E lives somewhere here. For example, at most it can be on C. This is my E. Now we go to the final part of this proof. We have A to C. Why A to C? Because I want to show that A up to C has property P. Now I hope that you agree with me. I can write it from A to E, union from E to C. Yes? From A to C is the union of from A to E, union from E to C. Okay? But one thing, I am sure that this has property P. Has property as P. Why? Because it is in E. E is in E. So this means that based on the definition of E, from A to E has property P. This has property P. What about this part?
It's in one.
It is from E to C, but from E to C is one part of this bigger interval, and this bigger interval is a subset of one of these open sets. So this means that from E to C is covered with one open interval. Covered with what? With O beta. So this is covered by finitely many open sets from my cover. This will add only one more cover at most to it. So if I ask you this union is covered by how many, you will say that this union is covered again by finitely many. And this union is equal to this. So this means this is covered by finitely many. And that is what I wanted to show. So this grants that this supremum is actually in E. The last step that I want you to study yourself is to prove this C is equal to B. The proof is very similar along these lines. Okay, and this will finally finish the problem. So you see that the difference is huge. So it was more or less obvious last time. Just after the definition, we were able to prove that this is compact. This is not compact, but this one, to prove that this is compact, we have to suffer a lot actually. So from now on, we learn that what you need to remember is that any closed interval is compact. Is that right? Okay. But it is not finished. I really want you, if you're interested in these kind of things, there is one more left. I have to show that C is equal to B, and then proof is by contradiction. You can assume that C is less than B and then arrive at a contradiction. Okay, so this is one of the most important results of this topic. There are three, so now we want to leave the general metric spaces. Of course, we left already. So this one is only in R. It's not a general metric space setup. So we were talking about intervals in R. And now there is one very simple and very powerful result, and that is that by looking at the sets in R, you can immediately tell it is compact or not. And because you see that the compactness is very hard to actually investigate, but if you know this theorem, it is extremely simple. Any set not in general theory, only a subset of R, Euclidean spaces. And let me read it for you. So let K be a subset of R, and that is important. I should have written it in red. So this is only for R. The following statements are equivalent. K is closed and bounded. K is compact. Every infinite subset of K has a limit point in K. So from now on, if I give you any set in R, you can immediately answer if it is compact or not. It should have two properties, closed and bounded. If it is closed and bounded, it is compact. You can completely forget about covers, subcovers, and things like that. But the only thing that we have to work in Euclidean spaces, R or R to any power K with the Euclidean metric. Okay? So I will not be able to prove all of it, but I want you to understand. The first thing is that there are three statements here. And you want to show that all these statements are equivalent. Okay? This is also good to know. How do you prove that three statements are equivalent? In principle, you should prove that these two are equivalent, one theorem. These two are equivalent, one theorem. And the first one and the last one equivalent, three theorems. Okay? You can do that. There is nothing wrong with that. But there is a more efficient way to do it. If I can prove that this implies that, and this implies that, and this one implies that, we are done. Yes? So instead of going back and forth locally, we can go in this direction. So this means that all of them are equivalent. So for example, because from here to here I can go forward in this direction, how can I go backward? I go here. So this means that this is a very nice way to prove that these three statements are equivalent. Okay, but I will not be able to prove it, but one of them might be is good. Why, if K is closed and bounded, it is compact? It needs a little bit of work. So K is closed, K is bounded. How can I conclude from only these two statements that K is compact?
It's a closed interval.
No, it is not a closed interval, because I can have a closed set which is not an interval. Yes, it is composed of intervals at the end, but it is not an interval, because interval should be connected. It should be one piece. So this is not correct that every closed subset of R is a closed interval, but it is related. So that is why boundedness is bounded. Yes. When K is bounded, what does it mean? It means it is a subset of a closed interval. If K is bounded, it might not be the case that it is itself is a closed interval, but it will be a subset of a closed interval because it is bounded. It cannot go beyond one threshold or cannot go below one. Yes? And now this one is what? Compact. We just learned. This one is what? Closed. Do you remember the theorem? If we have closed subset of a compact, it is compact. So this means K is compact. I don't know, 5.1 or 5.2. So K is compact. And so this one is done. From 2 to 3, do you remember what was it? It doesn't need even any proof. It is still on the board. You see, do you remember what was it? If K is compact and I have an infinite subset of my compact set, what happens? This will have a finite. It has a limit point in K. So here I know K is compact, and E is an infinite. So this is always true. This part, by the way, is not only true for R, but it was true for any metric spaces. So you don't need to prove anything, because this is a particular case of that general theory. So the hard part is this part. It's 2 or 3 pages. So I have written it, I have explained it in a very nice way, hopefully, that you can read and understand. Okay, so because the book has written it in a very, very brief way, so it might be that it's not easy to understand. So you can study this part yourself. Okay, but one slide is left. These are the names. So the equivalency between the first and two is called Heine-Borel theorem, usually. So it's good to remember the name. So statement 1 and 2, the equivalency of statements 1 and 2 is called Heine-Borel theorem for R. And I want immediately you know that even though this theorem in my notes I have explained this in R, but it could be also true for any R to power n with Euclidean metric. So exactly the same theorem will apply there. Okay, so because there is no time here, this is a very important example. Might be I can cover it next time. So it is very simple. I have completely written it in the notes, but this is the reason. This is important. I want you to know. Closedness and boundedness does not usually, in general, does not imply compactness in arbitrary metric spaces. Okay? But the other way around is always true. So if you know that your set is compact and you are still working in an arbitrary metric space, you can still conclude that your set is closed and bounded. But if you know your set is closed and bounded, but you are not working in Euclidean spaces, there is no guarantee that your set is compact. And the previous one is the example to this. Okay? There is no time to do that. I have written the solution in the notes. I really want you to study this one yourself. This theorem is also one-line proof, so you can read it there. So this is called Bolzano-Weierstrass theorem. big names, but this is very simple. It's just half a line of proof. So every bounded infinite subset of R has a limit point in R. This is nothing actually. It's a combination of the previous results, just one line. Any questions? Okay, so yeah, this is the last lesson we talked directly about metric spaces, and I mentioned next time we will talk about sequences, but you should also know about metric spaces a little bit. So that summary that I have written for you that's enough. So that information somehow you need to carry with you for the next lesson. Okay, not all of it, but the important results, the ones that actually I had time to go through during the lesson. Okay, so if you know those things, because it is important, otherwise you will not be able to follow. Okay, any questions? Okay, have a nice weekend. Thank you.